inside that box, then in that case also we say that the charges are continuous. So continuous charge distribution means that earlier what we have seen that there are one positive charge, two, three, four positive charges. We have seen this. So these individual or different charges, they are called discrete charges. They are called discrete charges. And if these charges, suppose if these charges are located like this, if these charges are located like this along a straight line, if these charges are located like this along a straight line, then what is this called? This is called continuous charge distribution. Continually these charges are distributed along a line. Understood? So in practice, we'll deal with charges much greater in magnitude than the charge on an electron. So we can ignore the quantum nature of charges and imagine that the charge is spread in a region in a continuous manner. So in general, we deal with charges which are not charges which have magnitude which is much greater than the charge on an electron. So we can consider that charges are continuous. Charges are distributed along a line or over a metal surface or inside a volume. So we can ignore the quantum nature of charges and imagine that the charge is spread in a region in a continuous manner. Such a charge distribution is known as a continuous charge distribution. Now, calculation of the force on a charge due to a continuous charge distribution. Okay, this is a theoretical topic. So we will study three types of charge distribution: volume charge distribution, surface charge distribution, and linear charge distribution. So three types of distributions are there. So we will study them properly. Consider a point charge Q naught lying near a region of continuous charge distribution. This continuous charge distribution can be imagined to consist of a large number of small charges dq. According to Coulomb's law, the force on point charge q naught due to a small charge dq is. So if we consider about, if we talk about this Coulomb's law, suppose we have a definite suppose we have a shape like this. We have a shape like this, and throughout this shape the charges are distributed uniformly throughout this shape. So let us consider a small charge element on this surface. So we are considering it like this, like a cube. So from that surface there is a small charge element, and the charge on this element is dq. D means small and q means charge, small charge dq. Okay, and let us consider that there is a point charge q naught here. So we will find out the distance between dq and q naught. We will find the distance between dq and q naught, and let us say that this distance is r vector. That this distance is r vector. Okay, according to Coulomb's law, the force on point charge q naught due to small charge dq is. So according to Coulomb's law, the force on point charge q naught due to small charge dq is df vector is equal to 1 upon 4 pi epsilon naught. Df vector is equal to 1 upon 4 pi epsilon naught q naught dq upon r square into r cap. Alright, so we want to calculate the force which exists between dq and this charge q naught. So we want to calculate the force. So because this charge is very small, this is dq, so the force which will exist between this dq and q naught will also be very small. So let us consider that force to be df. Df is that force. So 1 upon 4 pi epsilon naught, what we have by Coulomb's law, force can be calculated as 1 upon 4 pi epsilon naught q1 q2 upon r square. So 1 upon 4 pi epsilon naught q naught dq upon r square. R is the distance between these two charges. And r cap is a unit vector pointing from dq to q naught. R cap is a unit vector which is pointing from dq to q naught, because this is also positive charge and this is also positive charge, so positive will repel positive charge. That's why the direction will be from dq to q naught. Understood? By the principle of superposition, the total force on charge q naught will be, so if we are calculating a very small amount of force like df, and with the help of that small force we want to calculate the complete force which exists between this surface and this charge q naught, then we have to integrate this. So from a very small value of force, if we want to calculate the complete value of force, we have to integrate it. So f vector will be equal to integration of df vector. Now what is df vector? Df vector is 1 upon 4 pi epsilon naught q naught dq upon r square into r cap. Okay, so we will take out q naught upon 4 pi epsilon naught as constant out of the integration. So q naught upon 4 pi epsilon naught integration dq upon r square into r cap. This is what force which exists between this complete surface and this small charge q naught. Now, so is this clear to you?
Yeah.
Okay, do you have any doubt?
Can you play the diagram part again?
Okay.
Yeah.
Okay, this one, na? This one. Okay, so sometimes what we have seen that there are two charges. Earlier we have seen that there were two charges. One charge is this, suppose q1, and one charge was that, suppose q2. And what was the distance between these two charges? Was r. So the force which exists between these two charges was F is equal to 1 upon 4 pi epsilon naught q1 q2 upon r square. Now we are talking about a surface which is irregular in shape, any type of surface. So we have made randomly any type of shape. So we have made this shape, a shape, and from that shape we have taken a very small piece of charge. So we let us call this piece of charge to be dq, because it is very small. So if we take very small element, then we put a small d in front of that. So I have put it a d in front of q. So dq is a very small charge. Now from dq there is a charge q naught. There is a charge q naught which is outside this shape, and I want to calculate the force between dq and q naught. So that force will be 1 upon 4 pi epsilon naught. It will behave like q1. It will behave like q2. So dq q naught upon what is the distance between them is r square. So I have written small amount of force df is 1 upon 4 pi epsilon naught q naught dq upon r square, and r cap is the unit vector, because this is also positive charge, this is also positive charge. A positive charge will repel a positive charge. So the direction will be from dq to q naught. That's why I have taken unit vector along this direction, r cap. And with the help of this force, there are so many dq's inside this. There are so many this small types of charges inside this irregular shape. So there are so many charges, so many small charges. So if we want to add up all these charges, then we will get the complete force. We will get the complete force between this surface of charges and this q naught. So what will be the complete forces? For we have calculated df here, and with the help of df, if we want to calculate the total force, then we have to integrate df. So integration of df, what is df? 1 upon 4 pi epsilon naught q naught dq upon r square r cap. So q naught upon 4 pi epsilon naught is a constant which can be taken out of the integration. So if we do not have if we do not have discrete charges, discrete means different charges, then if we have continuous charges, for continuous charges, Coulomb's law will be written like this. Is this clear now?
Yeah.
Okay. Next is different types of continuous charge distributions. Different types of continuous charge distributions. So there are three types of continuous charge distributions. A is volume charge distribution. A is volume charge distribution. Now, it is a charge distribution spread over a three-dimensional volume or region V of space as shown. So it is a charge distribution as shown. So we define the volume charge density at any point in this volume as the charge contained per unit volume at that point. So in the case of volume charge distribution, we consider a volume where where so many charges, where so many small unit charges, so many small unit charges are contained in that volume. So let us make a diagram for that, for understanding what is volume charge distribution. I am drawing a random shape. You can also draw any type of shape. It is not required to draw the same type of shape which I am going to draw. Suppose that this is a bag. The shape of this bag is any kind of shape. Suppose that this is a bag, and in this bag there are so many charges which are filled inside this bag. So charges are plus, 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 plus. And from these charges, I will consider a very small unit, a very small volume, and let us consider that volume to be dq, and let us consider a small point charge is kept outside like this. What is the distance between dq and q naught? We will take this distance vector as r vector. So I am here I am defining a new term. A new term is volume charge density. What is volume charge density? Charge per unit volume is called volume charge density. Charge per unit volume means charge divided by volume. So volume charge density is defined as volume charge density is defined as, it is denoted by rho, and it is defined as charge divided by volume. So dq divided by dv, v is for volume here, dq divided by dv. So this is our equation number 1. Next, for example, if a charge q is distributed over the entire volume of a sphere of radius capital R, then its volume charge density is, for example, if we are talking about, for example, if we are saying that inside a sphere, the total amount of charge, the total charge which is filled up inside a sphere be q, then what will be the volume of that sphere? We know that volume of a sphere is 4 by 3 pi r cube. So volume charge density in that case will be q. Q is the total charge which is filled inside a sphere, and what will be the volume of the sphere? Volume of the sphere is 4 by 3 pi r cube. And what will be its unit? This is charge and this is volume. The unit of charge is coulomb and the unit of volume is meter cube. So it will be coulomb per meter cube. That's why I am writing coulomb meter raised to the power minus 3 coulomb per meter cube. Is this clear to you, Anusha? Till here?
Yes.
Okay. All right. Now let's move on to page number 26 of the notes. From equation 1, the charge contained in small volume dV is. So from equation 1,
So
tell me.
this rho is equal to q by 4 by 3 pi r cube. That's the final answer. Or
No.
we have to
This is an
more?
example. This is an example. I told you na that
Okay.
we can consider
Okay, I understand.
any shape. Okay.
I got it.
Okay. Now
Thank you.
page number 26 from equation 1, the charge contained in small volume dV is dq is equal to, we have rho is equal to dq upon dV. So dq will be rho into dV. dq is equal to dq is equal to rho dV. So force on Q naught due to entire volume V is, so force on Q naught due to entire volume V will be, so now we are going to calculate total force. So what will be the formula for total force? I have written over here. What will be the formula for total force? It will be force on Q naught due to entire volume V will be, so force due to entire volume. That's why I am taking the subscript as V. Fv vector is equal to Q naught upon 4 pi epsilon naught, Q naught upon 4 pi epsilon naught integration dq upon r square, and r cap. As we are integrating means adding up. As we are integrating the charges which are distributed all around the volume, which are filled up inside the volume. So we are writing a small subscript v. V means volume integral. Volume integral means कि I am adding up all the charges which are filled up inside any volume. That's why I am writing this subscript V. Okay. Now FV vector is equal to Q naught upon 4 pi epsilon naught volume integral dq, we will write rho dv upon r square into r cap. Is this clear to you? Tell me.
Yes, sir.
Okay. Now therefore electric field due to volume charge distribution at the location of charge Q naught. What is electric field? Electric field is force per unit charge. So we are calculating force on which charge? We are calculating force on Q naught. Because of this entire volume, we are calculating force on Q naught. So electric field will be F upon Q naught. Electric field will be EV vector. Electric field will be FV vector upon Q naught. FV vector upon Q naught means this is FV and this is divided by Q naught, means this Q naught will get divided by, this is 1 upon Q naught, and Q naught upon 4 pi epsilon naught volume integral rho dV upon r square r cap. This Q naught will get cancelled by this Q naught because I am doing, this is FV vector, and this is upon Q naught. So 1 upon Q naught into FV vector, I have written it like this. 1 upon Q naught multiplied by FV vector. So Q naught will get cancelled by Q naught. So 1 upon 4 pi epsilon naught volume integral of rho dV upon r square r cap. Now let us move on to the next type of charge distribution. So B, next type of charge distribution is surface charge distribution. So B is surface charge distribution. As it is clear from the name that whenever charges are distributed over a surface, whenever charges are distributed over a surface, then we call it as surface charge distribution. Surface charge distribution. It is a charge distribution spread over a two-dimensional surface S in space. This is a charge distribution which is spread over a surface. Okay, we define the surface charge density at any point on this surface as the charge per unit area at that point. Now, earlier in volume charge distribution we have considered a volume. Now, in surface charge distribution we will consider a surface area. Okay, so the shape of that surface area will be like this. So we have considered this surface. This entire surface is, and from this entire surface we have considered a very small element. We have considered a very small surface, and I am calling this surface as ds. I am calling this surface as ds, and let us consider that there is a small charge q naught here. There is a small charge q naught here. So the distance between ds and q naught, the distance between ds and q naught is r vector. The distance between ds and q naught is r vector. Okay, so what is ds? What is surface charge density? Like volume charge density, we have charge per unit volume. In surface charge density, we will have charge per unit surface area. Okay, so surface charge density is like this. Surface charge density is denoted by sigma. So sigma is equal to charge divided by small charge divided by small surface, dq upon ds. Like earlier, we have seen that volume charge density is denoted by rho. It is denoted by rho. It is given as dq upon dv. Similarly, surface charge density will be given as dq upon ds, charge upon surface area. Then this is equation number 2. This is equation number 2. And as it is very clear that this is Coulomb and this is surface area, what will be the unit of surface area? Unit of surface area is meter square. So SI unit of sigma is Coulomb per meter square. SI unit of sigma is Coulomb per meter square. Now, as we have taken an example of a sphere, so in the similar way, we will take an example here also. For example, if a charge Q is uniformly distributed over the surface of a spherical conductor, over the surface, now the charge is not filled up inside the sphere. Now the charge is distributed over the surface. So, what is the surface area of a sphere? Do you know? What is the formula for surface area of a sphere? Like volume of a sphere is 4 by 3 pi r cube. In the same way, the surface area of a sphere is 4 pi r square. So, if a charge q is uniformly distributed over the surface of a spherical conductor of radius r, then its surface charge density is sigma is equal to, what is the charge now? Q. What is the total surface area of the sphere? 4 pi r square. Q upon 4 pi r square. This is just an example. Is this clear till now? Okay, all right. Then from equation 2, the charge contained in small area ds is, from equation 2, I will say that dq will be sigma into ds. Sigma into ds. So here we were talking about the force due to a volume charge distribution. Now I will talk about the force due to surface charge distribution. It is Fs vector. Fs vector is q naught upon 4 pi epsilon naught. Q naught upon 4 pi. In the same way, we will write integration sign here. There, we were integrating the charges which were filled up inside a volume. So that's why I have written V here. Now, I am integrating. Integrating means adding up. I am adding up all the charges which are spread over this surface area. So I will write surface area here. I will write S here. S is for surface. S is for surface, and then dq upon r square, dq upon r square into r cap. And what is dq in this case? In this case, dq is sigma ds. So Fs vector is equal to q naught upon 4 pi epsilon naught integration of surface, and dq is sigma ds upon r square into r cap. Similarly, so like we have calculated force due to the volume charge distribution, similarly we will calculate electric field. So what will happen in the electric field? Like this, electric field due to volume charge distribution was 1 upon 4 pi epsilon naught volume integral rho dV upon r square. Now it will be electric field due to a surface charge distribution, it will be 1 upon 4 pi epsilon naught surface integral of sigma ds upon r square r cap. Simple. Is this clear to you, Anusha?
Yes, sir.
Okay. So we have three types of distributions here. So first type of distribution was volume charge distribution, when the entire charges, when whole charges, all the charges are filled up inside a volume. Secondly, we have surface charge distribution, when all the charges are distributed over a surface. Now thirdly, we will have line charge distribution, when all the charges are distributed along the line. None of the point on the line is left empty. All the line is filled up with charges. So C part is line charge distribution. C part is line charge distribution. So it is a charge distribution along a one-dimensional curve or line capital L in space as shown. We define the large line charge density at any point on this line as the charge per unit length of the line at that point. Alright. So like we have defined the surface charge density as sigma. Sigma is equal to dq upon ds. In the same way, we will define line charge density as lambda line charge density is denoted by lambda. So line charge density is lambda is equal to dq upon dl. dq upon dl. This is equation number 3. Now the SI unit for lambda is, it is also very much clear that this is dq. dq means charge, the unit of charge is coulomb. This is dl means length, the unit of length is meter. तो कूलम्ब अपॉन मीटर मीन्स कूलम्ब पर मीटर. SI unit of lambda is coulomb per meter. SI unit of lambda is coulomb per meter. For example, if a charge Q is uniformly distributed over a ring of radius r, over a example, if a charge is distributed over a ring of radius r like this, over a ring of radius r, then its linear charge density lambda will be all the charge, entire charge is distributed along the circumference of this, along the circumference of this ring. So Q upon what is the length of this ring? Length of a ring is its circumference. And what is circumference? Circumference is 2 pi r. Lambda is equal to Q upon 2 pi r. Tell me, is this clear to you?
Yes, sir.
Okay. Okay, now the charge contained in small length dl is. Now let us talk about the charge. So lambda is equal to dq by dl. So dq will be lambda into dl. dq is equal to lambda into dl. dq is equal to lambda into dl. So force on q naught due to the entire length L is given by. So in the same way, we are calculating the force due to the length, due to the line charge distribution. FL vector is equal to q naught upon 4 pi epsilon naught integration. Now we will write L. Now we will write L beneath this. Now we will write L near integration sign, and dq upon r square. So what we will write dq? dq will be lambda dl upon r square, r cap. Therefore, electric field, how electric field will be written? Therefore, electric field due to line charge EL vector is equal to, this q naught will get removed, 1 upon 4 pi epsilon naught line integral lambda dl upon r square r cap. Okay, so the total electric field due to a continuous charge distribution is, continuous charge distribution means, suppose we have a space where we have volume charge distribution also, line charge distribution also, surface charge distribution also. So total electric field will be, look, total continuous electric field. So E cont is for continuous. Total continuous electric field will be EV vector, electric field due to volume, plus ES vector, electric field due to surface means surface charge distribution, plus EL vector, electric field due to line charge distribution. EV plus ES plus EL, and then we are going to add up all these terms. So 1 upon 4 pi epsilon naught EV, 1 upon 4 pi epsilon naught volume integral rho dV upon r square r cap. All right, plus surface charge distribution 1 upon 4 pi epsilon naught surface integral sigma ds upon r square r cap, plus 1 upon 4 pi epsilon naught line integral lambda dl upon r square r cap. Now we are observing here that 1 upon 4 pi epsilon naught can be taken out common from these three terms. So E cont will be 1 upon 4 pi epsilon naught volume integral rho dv upon r square r cap plus surface integral sigma ds upon r square r cap plus line integral lambda dl upon r square r cap. So if there is a space, if there is a space in which if there is a space in which volume charge is also there, line charge is also there, surface charge is also there, and if the electric field, if they are asking about the electric field, then we will add up all these electric fields due to volume charge, surface charge, and line charge. Is this clear to you?
Yes, sir.
Okay. Okay. Now one more thing. Uh, on to page number 29. Come on, page number 29 of the notes. And let's leave this numerical for a while because it is a very big numerical. So it will take some time. So let's leave this numerical for 1 or 2 classes. After 1 or 2 classes, then I will come on this numerical also. Because before understanding this numerical, we have to understand Gauss law also. So first of all, I will do Gauss law, then I will come back on this numerical. Okay, so please leave page number 29, page number 30, and page number 31. Similarly, there is another numerical on page number 31. On the downside of page number 31, there is another numerical. We have to leave this numerical also. So please leave this, and let's come on page number 34, electric dipole. So I have left these two numericals. I will do these two numericals after completing Gauss law in electrostatics. Okay. So can you please wait for 2 minutes? I'm just coming back.
Okay, sir. No
Okay.
problem.
Okay. चलिए, now on page number 34, electric dipole. Electric dipole. A pair of equal and opposite charges separated by a small distance is called an electric dipole. A pair of equal and opposite charges separated by a small distance is called an electric dipole. Now, what is dipole moment? It measures the strength of an electric dipole. The dipole moment of an electric dipole is a vector whose magnitude is either charge times the separation. Times means charge is getting multiplied by the distance between the charges. Charge times the separation between the two opposite charges, and the direction is along the dipole axis from negative to the positive charge. So electric dipole is a pair of equal and opposite charges like this, minus q and plus q. If these two equal and opposite charges are separated by a small distance, and what we take this small distance to be, we take this small distance is 2a, 2a between these two charges. All right, and dipole moment is p vector is equal to q. Q is a scalar quantity, so we cannot put a vector sign on that. Q multiplied by 2a vector. So q multiplied by 2a vector, it is dipole moment. So dipole moment, the direction of dipole moment is from negative to positive charge. Direction of dipole moment is from negative to positive charge. Is this clear? I think that we have discussed it earlier also.
Yes.
Okay, so let's do it. Let's do it in detail with the chapter also. P is equal to q into 2a. The SI unit of dipole moment is the SI unit of dipole moment. This is called dipole moment. This is called dipole moment. What is this? What is its SI unit? This is q and this is 2a. 2a means distance. So q is coulomb and distance is meter. So SI unit of coulomb meter. SI unit of P is coulomb meter. Now, ideal or point dipole. Ideal or point dipole. Ideal or point dipole. A dipole in which size 2a tends to 0. This is called ideal dipole, where size is very small. So in ideal dipole, 2a tends to 0. 2a tends to 0 and q tends to infinity, means the value of charge is very large. The value of charge is very large, and the distance between two equal and opposite charges is very small. It approaches to 0. It approaches to infinity. Nothing can be exactly equal to infinity. That's why I am writing here that q tends to infinity. Infinity means it is a very large term. Okay, in such a way that dipole moment P is equal to q into 2a has a finite value. So P is equal to q multiplied by 2a has a finite value. Why? Because this q tends to infinity. Infinity means it is 1 upon 0 and 2a tends to 0. It is 0. So it means that if this charge is anything upon infinity. So if the value of charge is example x upon 0 and this 2a is 0, then its value will be equal to x only. Its value will be equal to x only. So when charge tends to infinity and distance between the two charges tends to 0, then we call such a dipole as an ideal dipole. Ideal dipole is only in the books. Practically, ideal dipole do not exist. Okay, Anusha, can we move further?
Yes.
Okay. Now, come on to page number 35. This is dipole field. The electric field produced by an electric dipole is called a dipole field. Now, electric field at an axial point of a dipole. Electric field at an axial point of a dipole. So consider an electric dipole consisting of charges plus q and minus q. We are on page number 35. Consider an electric dipole consisting of charges plus q and minus q separated by a distance 2a and placed in vacuum. Let P be a point on the axial line at distance small r from the center O of the dipole on the side of the charge plus q. So we are considering a dipole like this. We are considering a dipole like this. So on here charge is minus q, here charge is plus q. And the center of this dipole is O. What is the distance between these two charges? It is 2a. So if I am considering about this center, then what is the distance? This from here to here it is a, from here to here it is a, because this is the midpoint. Now I want to calculate the electric field at point P. What is the distance of this point P from this dipole? Whenever we calculate distance, of a point from a body, so we calculate the distance from the center of that body to that point. Whenever we have a big body and a small point, so what will be the distance between that big body and small point? So we will consider the central point of that body and the point. So distance between the midpoint and this point, let us consider it to be small r. Let us consider it to be small r. All right. Then for calculating electric field, we always consider that a small unit positive charge, means 1 coulomb charge, is kept at this point. A small unit positive charge, we consider that a positive charge is kept at this point. So what will happen now? This one is positive charge. This positive charge will repel this positive charge. We are considering, always we consider, whenever we calculate electric field, we consider that at point P, there is a positive charge. This positive charge is going to repel it. Positive is going to repel positive charge. So this is E plus Q. This is electric field due to this plus Q charge. Now, if we talk about this minus Q charge, this minus Q is going to attract this plus Q charge. So E minus Q. E minus Q. So this minus Q is going to attract this positive charge here. E minus Q is the direction will be, attractive direction will be here. Now electric field due to charge minus Q at point P is, let us talk about what will be the value of this E minus Q. E minus Q 1 upon 4 pi epsilon naught. 1 upon 4 pi epsilon naught. I am talking about the electric field due to charge minus Q. So we will not take the sign of this charge. Sign is always used to determine the direction only. In the value we put only the magnitude. So 1 upon 4 pi epsilon naught Q upon, what is the distance between minus Q and point P? This is small a, and from here to here it is R. So r plus a whole square. Is this clear, Anusha? R plus a
Yeah.
whole square, है ना? And we write the direction is towards left. Direction is towards left. So if I have written towards left, then I am not, then it is not required to write any unit vector like r cap, m cap, anything. It is not required to like that, write like that. Okay. Uh, then okay, and p cap, write p cap here. P cap means the direction of p cap. P cap means dipole moment. The direction of dipole moment is from negative to positive, but I have written towards left. So further we can write minus also, because the direction of E minus Q is opposite to P cap, opposite to dipole moment. Similarly, E plus Q vector is 1 upon 4 pi epsilon naught plus Q. So electric field due to this plus Q charge is Q upon, what is the distance between Q and P? R minus A. This distance here to here, the distance is r. From r you have to subtract this a. We want to calculate only this distance only. This is r minus a. So q upon r minus a is whole square p cap. Now due to this plus q, the electric field will be towards right, towards right. Okay. Now the net electric field, come to page number 36. So the net electric field means total electric field. E axial is equal to E axial is equal to E plus Q, E plus Q vector plus E minus Q vector. Okay. So when we add, then we require, when we add two vectors, then we require unit vector also. Now what is E plus Q? It is 1 upon 4 pi epsilon naught, 1 upon 4 pi epsilon naught Q upon r minus a is whole square p cap. Okay. Now E minus Q, 1 upon 4 pi epsilon naught Q upon r plus a is whole square, but it is towards left. E minus Q's direction is towards left, so it is opposite to P. Dipole moment's direction is from negative to positive. So this E minus Q is from here, oppositely directed. So we will write minus P cap here. I will write minus P cap here. Is this clear why I have written minus P cap here? Is this clear to you why I have taken minus P cap here?
Yes, sir.
Okay. Now let's, if you have noted down till here, then can I move to the next slide?
Yeah.
Okay. Now 1 upon 4 pi epsilon naught, 1 upon 4 pi epsilon naught and Q. These terms are common. P cap is also common. So what is E axial? Is equal to, E axial is equal to Q upon 4 pi epsilon naught, Q upon 4 pi epsilon naught 1 upon r minus a's whole square 1 upon r minus a's whole square minus 1 upon r plus a's whole square minus 1 upon r plus a's whole square and p cap. And I have taken common p cap also and I have written it after the bracket. Okay. Then this one is q upon 4 pi epsilon naught. Let us take the LCM. Whenever we take LCM, we will multiply both these terms and r plus a square will be multiplied by 1, r minus a square will be multiplied by this one. So r plus a whole square minus r minus a's whole square upon r minus a whole square into r plus a whole square, and after the bracket we have to write p cap. Now q upon 4 pi epsilon naught r plus a whole square, so r square plus a square plus 2ra minus r square plus a square minus 2ra. In the denominator, r minus a into r plus a's whole square, r minus a's whole square and r plus a's whole square. So we can write them together like r minus a into r plus a's whole square. Okay, and p cap. Now q upon 4 pi epsilon naught r square plus a square plus 2ra minus, if we expand it, so minus sign will get multiplied inside, minus r square minus a square plus 2ra upon r minus a into r plus a is r square minus a square, so whole square. Whole square is at its place. R minus a into r plus a is r square minus a square. P cap. R square minus r square, they will cancel out each other. A square minus a square will also cancel out. 2ra plus 2ra is 4ra. So q upon 4 pi epsilon naught 4ra upon r square minus a squares whole square and p cap. So we can write it like this also, 1 upon 4 pi epsilon naught q into 2a into 2r. Understand it? 2a into 2r is 4ra. So q into 2a into 2r upon r square minus a squares whole square p cap. What is q into 2a? Q into 2a is dipole moment. It is p. So E axial vector is 1 upon 4 pi epsilon naught q into 2a is p into 2r upon r square minus a squares whole square into p cap. Now what is p into 2r? We can say that because dipole is a very small electric dipole is a very small object. It is a very small object. The basic definition of electric dipole is that the two equal and opposite charges are separated by a very small distance. Very small distance means this 2a is very less than r. It implies that a is further less than r. 2a is less than r, then what is a? A is half of 2a, so a will be further less than r. Therefore, a square can be neglected. So r square minus a square is approximately equal to r square. R square minus a square is approximately equal to r square. Therefore, E axial vector is equal to 1 upon 4 pi epsilon naught 2 p r upon a square is 0 now. A square can be neglected. Neglected means A square is approximately equal to 0. So R square's whole square. What is R square's whole square? It is R to the power 4 P cap. Now 1 R will cancel out by this 1 R. So E actual will be 1 upon 4 pi epsilon naught 2p upon R cube into P cap. Is this clear? Is this clear? Anusha, are you there?
Yes, sir.
Okay, so we have done electric field at an axial point of a dipole. Now equatorial point we will do in the next class. All right. Okay, Anusha. So now is this 9 p.m. there?
Huh?
Is this 9 p.m. there? 9 p.m.
No, yeah, it's 9 p.m. here.
Okay, okay. It's 10:30 here. Okay, Anusha. Bye bye. We will meet on Monday.
Okay, sir.
Okay. Okay. Bye bye. Bye bye.